So in the previous lecture, we talked about axiomatizing the Bussy set and formalizing the Bussy set as a set that contains an element or elements such that these elements are an element of intersection between two or more sets. Today's lecture, apologies for the noise. Today's lecture, I will be defining breedability and submissiveness. So we're going to talk about submissive and breedable femboys. Now, there is an important distinction to be made between these two types of femboys. So, by definition, submissiveness is the quality of being submissive, submitting to the request or command of a superior or dominant person. In other words, deference, submitting to the espoused legitimate influence of one's superior or superior. And breedable is the ability to be bred, able to breed or be bred. And I don't think I need to define further what breedable means. Now, there is an important distinction to be made between these two guys, and that distinction is that they are not equal. These two are not the same. Right? Most important thing I need to state about these two is that they're not the same. Both are states, yes, but they are not colloquially the same. So, when we say that a femboy is submissive, we are taken to mean a femboy that is willfully capable of doing almost, if not all, the things we ask him to do or command him to do. If we were to take a maid outfit and give it to him and tell him, wear this, he will wear it if he is submissive. Now, when we say a breedable femboy, we are taken to mean a femboy that is at an extreme ability to reproduce and commence intercourse with one that can be bred at any time, anywhere. So, in short, the former talks about will, while the latter talks about ability. Now, since we have defined this, let me make a small diversion, a small connection to the previous lecture. If we take submissiveness to be a set A, or I'm just gonna use S, and breedability to be equal to B, then these two have qualities that would prove that they contain a Bussy set. So, this is a Q, such that Q is an element of the intersection. And thus, there exists a Bussy set, such that Q is an element of that Bussy set. Okay? So this is basically telling us that there exists an element between these two guys wherein this guy is part of their intersection. So if I were to draw a Venn diagram over here, Q would be part of this region over here that I just shaded. Q would be part of that. And since Q is part of that region, there exists a Bussy set wherein Q is a part of that Bussy set. Anyone got that? Now, what next? Now let's consider trying to make a graph that represents both these guys but describes both of these guys with respect to a third quality, like time, or third variable time. Now this is not possible because these guys, their very nature does not align with each other. Their very natures are different. So if we try to say that this axis denotes submissiveness, so this top here, very submissive, here, very dominant, alright? Now if we were to make a graph for the submissiveness, it fluctuates. I'm going to use a fluctuograph, for example. Yes, we were able to do that, but how will we describe? We cannot describe breedability here. Because these guys, these axes, their purpose is to give us a language to represent the submissiveness, not the breedability. So if we try to graph, I don't know, breedability for some reason, it's not going to be possible. We can't do this. Because the axes over here are meant to describe or denote the submissiveness or dominance of the person or the specimen. So it's not possible to graph them at the same time and describe them with respect to a third variable. But we can, however, we can describe one of them with respect to the other. So if we let submissiveness equal S, and if we let B, like a while ago, just let it small case B. This is not a set. I'm not saying that these guys are sets, but quantities, variables. B. From there, you can say that both these guys are proportionally have direct proportionality or inverse proportionality. Small crash course or review in high school mathematics if you guys did not listen to the teacher. When we say that these two are directly proportional, they are equal with a constant. I'm not using A, this is K. KD. So this is equal to constant. So S, as S increases, B increases by a factor of K. You got that? So B's increased the same rate as S, but K is multiplied to B. So they're not entirely equal. So we're saying that the submissiveness is equal to the breedability but scaled by a constant. So their graph is linear, like this. If we were to have S here and B is this axis, it would be like that. That would be our graph. It would be linear. As one increases, the other one increases as well. It does not decrease. When we say that S and B are inversely proportional, this means that S is equivalent to the reciprocal of B times K over B. And so for here, we can say that S times B is equal to a constant. Okay? And from here we can say that B is equal to K over S, which is just equal to that. And when we say that these guys are inversely proportional, as one decreases, the other one increases. So the opposite happens for one as the other goes down or goes up. So if we were to graph it here, I'm going to use this equation here. So S is a function of B. So this is the S, this is Y, this is our X. It would be like this. Or it could be the other way, like that. Like that, it could be like that, but it's mostly like this. So as we notice, as B increases, as the breedability increases, the S, the submissiveness, decreases. And as the breedability decreases, the submissiveness increases. So what we're saying here is that the femboy becomes less submissive as he becomes more breedable, as he is more able to perform intercourse. He becomes less submissive and starts becoming dominant. Alright? But it doesn't actually become dominant. It just approaches it, because this thing shoots off into infinity and doesn't touch B. It doesn't stop. Alright? So, yeah, it's that. But I need you guys to note that these guys aren't the only conditions for mathematically modeling or representing one with the other. There are cases wherein S would equal B. Wherein as the submissiveness increases, the breedability equally increases with nothing scaled to it. It doesn't decrease, it doesn't do anything. It just does exactly what is done, or what S does. If S increases, it increases as well, with no caveats. And actually, this is actually the great majority of femboys are described like that. As their submissiveness increases, their ability to breed increases equally. I can be mauled that way. Now that we've made that abstraction, a brief algebraic abstraction, how do we solve the enigma from before about describing these two simultaneously with respect to time? Now, I've established already a while ago that we cannot graph these guys with respect to time on one dimension. I was using only, I'm not one dimension, I was actually using 2 dimensions. And 2 dimensions can only describe 2 quantities with one respect to the other. We can only describe y equals f of x. Y is a function of x. And the inverse, which is just a 90-degree rotation. So, let's take a small dive into the world of electromagnetism. The wonderful mathematician James Clerk Maxwell. James Clerk Maxwell, the author of the Maxwell's equations. It's named after him. He was the one who made them, for Christ's sakes. He established that electromagnetic waves can be described as fluctuations, as waves actually. Yes, there are waves, for Christ's sakes. But not only that, it is described as a 3-dimensional wave wherein the 3rd dimension is time. So this dimension is for the electronic force. E is not Euler's number. And this dimension that's slanted is the 2nd dimension. That is the magnetic force. And this 3rd dimension is time. And from there, we can describe both of these with respect to time. Hooray! Enigma is solved. There. The shaded regions is the magnetic force, which is described in a 3-dimensional manner that is perpendicular to this. And we got that. I think I want to post a video that describes this using manim so you guys can get a better visualization of this. I'll see if I can do that. If I can, I'll definitely put it in the link in the course syllabus so you guys can understand, or the link on the video. I can edit that. So we can use this. We can do this tactic to describe both of them with respect to time, and thus with respect to each other. So it solves everything and makes everything a whole lot better if we visualize these guys as a 3-dimensional thing, or coordinates. So from there, we can copy that and say that this z-axis is for s, this x-axis can be for b, and this axis for b can be for t. So we can describe these guys with respect to time. Don't you think that's neat? That we're able to actually use or apply real-life concepts such as electromagnetism in order to describe these guys and solve our enigma. It's just an example graph. And so, yeah, it's amazing. Now, what I said a while ago, that these guys cannot be measured at the same time simultaneously, or described at the same time simultaneously, we have actually drawn a very close thing to quantum mechanics. We have drawn a very close connection to quantum mechanics and the Heisenberg uncertainty principle. I'll discuss that in the last lecture. So that ends this lecture. So next lecture will be about catboys and twinks. I just wanted to make a quick announcement that we are hiring professors. LOSC is hiring professors. You guys can email your applications to me, and I'll see if you guys can do it, and your desired subject. And I'll put it in. I'll link another docs to the courses we teach here. So that's it for me, Professor Suck, and I'll see you guys in the next lecture.